Hope you guys are doing well. I was just telling you that we have a special request today to do limits and infinities. So buckle up. Let's get to it. So what you have is we're gonna start with a sequence. And you guys know what a sequence is. A sequence looks like 1, 2, 3, 4, 5, etc. So the particular sequence I'm interested in for our purpose today is the sequence that goes 1 over 1, and then 1 over 2, and then 1 over 3, and then 1 over 4, etc. In general, this is 1 over n. And why am I interested in this? Because we need to get something immediately out of the way whenever we're talking limits, which is that mathematics and the real world are different. So here I have my phone, for example, okay? If I divide my phone in two, I will have two pieces. And then if I take one piece and I divide that in two, and I divide that in two, if you want a piece of paper, right? If you take this piece of paper, you fold it in half, and then you fold it in half again, and you fold it in half again, you will find that after a certain point, if you keep shredding it, you will find that at a certain point, you cannot shred anymore. And if you want to even keep going, you will get to the level of an atom, okay? And then you will not be able to divide the atom. Well, okay, let's assume that we're going to create a nuclear disaster and split the atom in two. Fine, let's split the atom in two, but then you get the fundamental particles, the protons and the neutrons and the whatever. And splitting those in two requires a whole apparatus, you have to go to CERN to do it. And even when you do it, you're going to still end up with something that is indivisible. And these particles, they become waves at that level and so on and so forth. So the real world is complicated that way. But in mathematics, you can divide something forever. So if you notice here, for example, let's do some trick. So let's draw this square, okay? And then I can take just this one, okay? But then I can zoom in and I can divide that in 4 and then take this part here, okay? So let's color the others. And I can zoom in further and I can do this and then take that small one. And if my tablet supports it, I can keep zooming on forever. And I can keep doing this division in math forever and taking the small circle square here in the bottom and so on and so forth. I can keep doing that forever, okay? So what I'm trying to do is forever. So thing number one here that we need to get out of the way. Forever exists in math. Forever doesn't exist in real life, but forever exists. And we're gonna call this forever infinity. Okay. It's here. We need to have that in our lives. That's it. Let's get that out of the way. Now, there are many ways to count to infinity. That's the thing, but you can never get there. That's the other thing. Because we live in the real world, and because we are doing mathematics in the real world, but we know that conceptually speaking, you can't keep doing something forever. Some processes just never end. Like the process I just showed you before with taking the small square, or dividing the paper in two, or the process that we have here. Okay, so this process will just not end. Where is the last point in this? Nowhere, okay? I can keep saying 1 over 10,000 here. Okay, yeah, but there's 10,001, 10,002, 10,000, okay, a million, 10 million, the 10 to the 100, a Google, and you can keep going here. There is no end point here. There's no wall where you will hit. Okay, you can just keep going forever. Now, we have two things that sound weird when they've put together. So number one is we can go forever. Okay, and number two is we can't go forever. Right? We can't go forever. And then here it is because no time. No time. Not enough energy. We can't. in the real world go forever. But conceptually, we can't go forever, just like in this case, okay? So here, this is 1 over n. So I need a mechanism to allow me to guess what the process will do when I let it go forever without actually going myself forever. Does that make sense? Let me say that again. I cannot go forever myself because I will die before this ends. But I need a mechanism, since I know that this exists. I need a mechanism that allows me to guess what the process can do if left running forever, without actually myself running it forever. Okay? And that process is called limit. And this is what we really need to know and we really need to do today. So the solution for this apparent paradox here is limit. What is a limit? Essentially, if you keep, let's plot these numbers here, okay? Let's do that. So here we have the number line. And this will be our 0. And this will be here number 1. Okay. And let's plot these numbers right here. So the first one here will be number 1. Okay, that's 1. The next one will be 1/2. That's 1/2. The next one will be 1 over 4. Sorry, 1 over 3 before 1 over 4. So 1 over 3 here. And there's 1 over 4. And here we have 1 over 5. And let me zoom in. Here you will have approximately here 1 over 6. And here you will have 1 over 7. And 1 over 8. And 1 over 9. 1 over 10. And they keep stacking here. These are the members of this family, the family 1 over n. We can take any other family for that matter. I'm just taking this as an example. Question. Do we have any member of this family in this zone right here? To the right of number 1. Do we have any member of that family over here? Can it happen? It cannot. Why? Because we notice that every time the numerator decreases, yes, you're absolutely right, Almahad, it cannot happen. Why? Because every time this numerator here, sorry, the denominator here is increasing, okay, because it's 1 over n, the more this denominator increases, the function decreases. I'm dividing by a bigger number. So the biggest number has to be the first guy. And so there's nothing after that. Fine. Is there any members of this family to the left of 0? No again. Why? Because all of these are 1 divided by a positive number. If it's y divided by a positive number, then it cannot be negative, can it? So there's nothing here, there's nothing here. All of this blue family is concentrated between 0 and 1. All of them live here. Okay? We have a decreasing sequence. It's going down. And the more it goes down, because it can go forever, the closer it will get to it being 0. It's closer and closer to hitting this wall here, but it's never touching that wall. Why? Because if 1 over n is equal to 0, this means that 1, if I multiply by n on both sides, 1 is equal to 0 times n. And this can never be the case. This is impossible. So I know now that none of those can be 0. But I know that I can get infinitely close to 0. Is there a number here where I can stop and say, oh, look, there's a millimeter between me and 0? No, because you can always divide that interval in half. You can always divide more and more. You can always increase this n here. This n here can keep increasing, and then you will, at some point, fall inside this red interval that you've assumed before that can... what happened here? That it cannot get any lower. You will keep getting infinitely closer to 0, never touching 0. And since we can, here, since we can get infinitely closer, and this is important, to 0, and never touching 0, we call 0 the limit of the sequence. This is a sequence that is decreasing, and it has, we call it a lower bound. Okay, a lower bound is just a place where it cannot get lower, just like here. It cannot get lower than 0. So it's going down all the way, all the way, all the way, all the way. It's becoming smaller and smaller, smaller and smaller, smaller and smaller, but it's never hitting 0. I don't need to go to infinity to know that 0 is the limit. I'm gonna keep getting infinitely closer to 0 as I go down. And so this is what we write. I say the limit as n is going to infinity, because remember, this guy is 1 over n, and n keeps increasing. Is there any limit on n increasing? Is there any bound? Is there any, no. N can keep going, 1, 2, 3, 4, 5, 10 billion, it can go to infinity, literally. So I don't need to go there myself. I'm gonna say limit of n goes to infinity of the sequence 1 over n. What is it? It's 0. And this is very intuitive, if you grab your calculator, okay? Just grab the calculator, take 1, divide by 2, for example, and then keep dividing by 2. And just answer divide by 2, divide by 2. Okay? If you keep dividing by 2, you will find yourself after a certain point, if you keep hitting enter, hitting enter, hitting enter, you will find yourself at some point, with a very small, I'm not sure if you can see it. You will find that this number is getting smaller and smaller, smaller and smaller. And the more you hit enter, the more it gets smaller, the more it gets smaller. You can play with this, you can put it on Excel. But you will find that you're going to always stay positive because we just proved it. Okay? And so the limit is literally 0. Okay? So this is what the limit is. I'm guessing what happens at infinity without actually going there. And I need this because I need to know. I want to know what happens. Why do we need to know what happens? Stay with me. But now that we've discovered this, let me ask you, what is the limit? By the way, we don't write the whole word limit. We just write lim. What is the limit as x, let's stay with n for now. As n goes, let's say, to infinity of n squared. What happens if I square numbers and I let my number go as big as I want? What's the answer for this limit? Yes, absolutely. It's infinity. Very good. I let n increase as much as possible. What happens to its square? Well, n squared is bigger than n whenever n is bigger than 1, right? And if this goes to infinity, then this also goes to infinity. Easy. Okay? What happens when I let the limit as n goes to infinity of 1 over n squared? Zero, absolutely. Just like this case here. Same case here. When I'm dividing by a bigger and bigger number, I am hitting 0. I still am positive because n squared is positive. And I cannot go lower than 0. I cannot go to a certain number and stop, because whatever number I stop at, there is one smaller. So I'm going to keep getting infinitely closer to 0, never touching it, which is why we call 0 the limit of this sequence. I'm going to ask you a question. Let's see. Which one do you think hits 0 faster? This guy, 1 over n, or 1 over n squared? They both go to 0, obviously. Which one do you think hits 0 faster? Neither of them had 0, so I'm not sure, but I don't think we can say either of them does first. Oh, neither of them hits 0, we both agree, because for them to hit 0, it's gonna need an infinite amount of time. But I can tell you which one is faster. I can totally tell you which one is faster. And let me show you before I tell you. Okay, so here I have plotted the 1 over x in green, which is the same as 1 over n, and I have plotted 1 over n squared in red. Notice that the red line is below the green line. Of course, they meet at this point. Can you guess what point it is? Of course, it's 1. 1 over 1 squared is equal to 1 over 1. Okay? But notice that the red line, when you go from 1 onwards, it goes less and less, less and less, less and less, faster than the green one. They both are limited between 1 and 0, right? Here you see it go bigger than 1 because this is a continuous function. So they're counting decimals as well. But if you ignore everything below 1, you know what? I'm gonna do it. If you count from here, okay? So they are both bound between 0 and 1, but we see that the red line goes below green all the time. So I can totally tell you which one is faster. N squared is faster. Okay. What is the limit as n goes to infinity of n plus 1 divided by n? Okay. Let me remove this out of our face. What happens if I take 2 over 1, 3 over 2, 4 over 3, 5 over 4? What do you think happens? gets closer to 1, absolutely. Absolutely. If I make a list of these things, over here I'm gonna make the list. 2 over 1 is 2. 3 over 2, however, so n plus 1 has to be always greater than 1. The numerator is always greater. This is 1.5. And then 4 over 3, this is 1.3 bar. And then 5 over 4 is equal to 1.25. And then 6 over 5, this is 1.2. And 7 over 6, this is 1.16. And so on. This number keeps decreasing. Okay? And as it decreases, it's going to hit 1 at the end. It looks like it's going to hit 1. Well, let's see if that makes sense. Can n plus 1, let me change color here. Can n plus 1 over n be smaller than 1 ever? Or equal, by the way. Let's start with equal. Can it ever be equal to 1? No is the answer. Why? Because if I multiply by n on both sides, I get n plus 1 equals n, which is never the case. So that's out of the question. Let's see if n plus 1 over n can get below 1. No, for the same reason, because you get this, which is also a contradiction. So I am going down, I am decreasing, and I am hitting this floor that this time, instead of 0, it is 1. So it looks like the limit is 1. Okay? It looks like our limit is 1 in this case. Let us see if this makes sense. If we can guess it without doing all this work. Okay? So if we have, this was the question, limit as n goes to infinity of n plus 1 over n. This was the question. Now, I'm going to say this is equal to the limit as n goes to infinity of n over n plus 1 over n. Can I not do that? It's the same denominator, so I can split them. But now watch what happens. I already know the answer of this guy. I already know the answer of this guy. If I keep dividing by a bigger and bigger number, I get 0. Okay? So here, this guy, as n goes to infinity, becomes 0. And so we get that this is equal to n divided by n. And what is that? 1. We don't need to go do that work anymore and count the numbers and have big lists and so on and so forth. All I need really is to be a little bit intelligent. As I'm dividing, mind-blowing, it is actually, it's very crazy. This idea is so rich. Now, of course, I'm using notation here, so I'm not doing it exactly the correct way. I'm going to show you how to do it formally, you know, but I'm just showing the idea. So if someone is watching on YouTube, just be careful. Don't do exactly what I'm doing. I'm just explaining. This kind of writing here is kind of not true, but okay, it just gets the idea right. Now, if I was to confirm with the computer, give me a second here, because my chat is in the way. Okay, here it is. So here I'm gonna type x plus 1 over x. And I'm gonna type, let you guys see what I'm doing. And I'm gonna type here y equals 1. And look, So this is our n plus 1 over n, or x plus 1 over x, same thing. And it's going down. It starts here at 1 for us. You can start anywhere, it doesn't matter. And it keeps going down, keeps going down, keeps going down, and gets closer and closer to this line 1 here. But it never touches it. Look, I can go as deep as you want. And even when I go very far and it looks like I'm touching, well, the beauty of computers is that I can zoom in and look, I'm not touching. Why I'm not touching? I just proved that it can never happen. Look, the proof is here. Okay? The proof is right here. It cannot touch 1. It cannot be less than 1. And so here we are still above 1 all the time. Okay? And that's it. I don't need to go to infinity. I don't need to even go to number 2. Just knowing what the sequence is and what the sequence, or the function for any matter, looks like, I can guess what will happen now. And that's exactly what we want. That's exactly what we're looking for. I'm looking for a way that tells me the answer without actually going there. Now, let's try one more. What is the limit as n goes to infinity? Let's keep n going to infinity. And let's do n squared minus 1 divided by n here. Try first of all to take a few examples, see what's happening, because we are still new to this. And then try to imitate what I did in the first case, where I found a clever trick that will save me time. Does it keep going up to infinity? Ooh, let's see. Let's see. I think that's a good guess. And I have this intuition because I'm looking at the numerator and I'm seeing this square here and I'm seeing power 1 here. So I'm guessing because we're going to infinity, the square will push faster, because we just shown that n squared is faster somewhere up there. We just showed that n squared is faster than n and going to infinity. And so I'm guessing that the numerator will grow faster than the denominator and it will boom up. Let's see if we can make sense of this. This is also the limit as n goes to infinity of n squared divided by n minus 1 over n again. Oh boy, we know what happens to 1 over n. When it goes to infinity, this becomes 0. So the larger and the larger the number n becomes, the smaller and smaller 1 over n becomes. And if I let n become infinity, which is what I am doing here, this becomes literally 0. Okay? And so we're left with the limit as n goes to infinity of n squared divided by n. And what is n squared divided by n? This is the limit as n goes to infinity of just n. because n squared divided by n gives you n. And so what is that answer? When n goes to infinity, what happens to n? It goes to infinity, right? Absolutely correct. Okay, so again, am I still taking examples? Am I still, I don't need my calculator. I don't need I can cleverly figure it out. I can cleverly doing some tricks figure it out. And here we can do the same thing. I can show you what happens on my graph if it cooperates. Okay. This is what we have. So this is x squared plus 1 over x as it goes to infinity. This black line here was the line y equals 1 that we had before. Look at this and tell me where is it going. Well, that's blowing up, isn't it? I'm gonna zoom out for you, look. It's blowing up. It's not stopping anywhere. Okay? And I can prove it. Because I know that n squared plus 1 over n is increasing. Simply because it boils down to becoming n. Okay? Well, n squared minus 1 actually. By the way, quick question, now that I made that mistake, what happens if I had a plus here? What do you think? Does it change anything? Right? I am adding a plus 1 when I already had infinity. So when this quantity here was smaller, when it was n squared minus 1, it still went to infinity. Now plus 1 will not go to infinity. What are you talking about? Of course it will. Plus, if you notice here, if this minus becomes a plus, then this minus here becomes a plus, and you're still adding 0. So as Alma said, infinity plus 0 is still infinity. Doesn't participate. And so here you look at this and you say, well, the biggest degree is the main player here. If this was n cubed plus 1 or n cubed plus n over n or whatever, it wouldn't have changed a thing. Okay? Because the biggest degree is the main player. Let's make another one here just before we get into what derivatives are. So if you just do this, limit as n this time goes to 0, and I'm gonna keep n, I'm not bothered. But I don't want you guys to focus on natural numbers anymore. I don't want to move 1, 2, 3, 4, 5. I'm going to allow myself to do 1, 1.5, 2, 2.3. I'm going to allow myself to become a real number. Okay, which will not change anything. I'm still going to infinity. Okay, so I'm going to call it x this time, because I want to move from sequences to just calling continuous things. So as x goes to 0 of let's say x squared minus 1 over x, which is the same one that we had here, okay? So originally here this was a minus, and this was a minus. It's the same one that we had up there, but I just changed it to an x, simply because we're taking now a continuous sort of steps. We're not going 1, 2, 3, 4, 5, which doesn't change anything. So instead of going to infinity this time, we're going to go to 0. Let's see if that changes. What I mean by going towards 0 is getting smaller and smaller, smaller and smaller, just like the first example we saw. Okay? Just like this guy. 1 over n becomes smaller and smaller until it hits 0. Let's imagine that x is going down until it becomes 0. Does it go to minus infinity? I don't know about that. What's happening is x squared is becoming smaller as x goes to 0. And x is becoming smaller as well as x goes to 0. Now, which one is faster in getting smaller? Is it x squared or is it x? Which one becomes less, faster? They both decrease. If x becomes smaller, then x squared will become smaller. But which one of them is faster? X squared is faster, of course. And if x squared is faster than my numerator here, which is the thing on the top of the fraction, this guy is decreasing faster than the x. Okay? So I'm expecting something that has to do with a small number. I'm not expecting infinities here. Okay? So let's see what really happens. This is the limit as x goes to 0 of x squared over x minus 1 over x. And now I have to pay attention. Before, I used this trick to say when n goes to infinity, this goes to 0. But now I'm not going to infinity, I am going towards 0. What happens to 1 when I divide it by a number smaller and smaller and smaller? 1 divided by 1/2 is 2. 1 divided by 1/10 is 10. 1 divided by 100th is a 100. And so on and so forth. I'm talking about 1 over n or 1 over x as x gets smaller, which is what we have here. X goes to 0. If x is getting smaller, what happens to this guy? It gets bigger and bigger. And if x gets the smallest, which is 0, this becomes the biggest, which is infinity. So here we already have a negative infinity here instead of the 1 over x. And here on the left, what do I have? Here on the left, instead of x squared over x, I have an x only. And what happens when x goes to 0? Well, this is equal to 0 minus infinity. And the answer is indeed negative infinity. Bravo, absolutely correct. So because the numerator is getting smaller faster than the denominator, it looks like I'm dividing a smaller and smaller number by a bigger and bigger number. But with a negative sign in front of it, it becomes very big, but in the negative, which is very, very, very small. This is the smallest you can get, minus infinity. It's all the way to the left of the number line, right here. Okay? And again, we can go back, which is not a necessary step, but I like to do it because we're having fun. We can go back to our electronic calculator. We can ask it to graph x squared minus 1 over x for us. And I will show you what happens when this guy hits 0. So, this is the function in green. And it's going down, it's going down, it's going down, you see. And look, it's not touching 0. It looks like it touches 0, but if you zoom in again one more time, it's not really touching. Okay. And then you can go down and you can see that whenever you go down, even when you reach very, very, very low, it's still very parallel to the y-axis almost. It's not touching the y-axis because I cannot be 0. It's a funny looking function, by the way. Okay. I shouldn't be doing this. This is cheating. We're letting the computer do our work. But we guessed it right. It keeps going down. And the closer we get to 0, the more it goes down. Whenever this happens, right? Whenever something like that, so it's getting next to 1 or next to 0 or something that looks like that, we call it, and I'm going to put this in red, asymptotic behavior. Asymptotis in Greek means getting closer and closer, which is exactly what we're doing. I'm getting closer and closer to minus infinity. I'm never going to reach it. I'm getting closer and closer to infinity here. I'm never going to reach it. I'm getting closer and closer to number 1 or getting closer and closer to 0 here, but I'm never reaching it. Okay? And so this is what we call asymptotic behavior of a function. We will revisit that idea a little bit in the future. So this is the story of limits, and this is the story of infinity. Infinity is part of mathematics because conceptually we want to keep doing things forever. When I divide numbers by 2, when I raise something squared, when I can technically do this forever. And this is not an easy idea, it's a sophisticated idea. If you go back to history, people were not comfortable doing this. But now we are. I think you can imagine something going on forever. That's not a very sophisticated, difficult thing for us to do. And since infinity is part of our life, we need ways to figure out what infinity is doing without actually going there. And so we invented this clever tactic, which is what we call limits. And this clever tactic allows me to go to the infinity without actually going there. I'm going to ask the function, what happens if I let you go forever? And the function is going to let me know, oh, if you go forever, this and this will happen. Okay? Notice, for example, that here in this case, I don't have to go to infinity every time. I can say what happens next to 0. And why am I interested in 0? Well, because here, if you let this go to 0, what's happening here? This x is becoming 0. And is it allowed to divide by 0? Big mistake. Never allowed to divide by 0. Why is it not allowed to divide by 0? Is it because it's in the 10 Commandments? No. Because what happens when you divide by 0? We just did it over here a second ago. When you divide by 0, you create infinities. And infinity is not a number. That's why the calculator says math error when I divide, let's say, 1 by 0. Okay? So if you hit 1 by 0, you will get math error on every calculator. Why? Because this process literally takes forever. It's a process that never ends. I'm saying 1 divided by 0. How do I know what that is? This is 1 minus 0 equal 1, 1 minus 0 equal 1, 1 minus 0 equal 1. I'm basically asking myself, how many zeros can I take out of 1? Well, the answer is infinitely many times. And this is exactly what we just said here. You can do it infinitely many times. So that's why the calculator cannot go there. It cannot say infinitely many times. But we are very, very comfortable writing this ourselves and saying the limit, for example, as x goes to 0 of 1 over x is equal to plus infinity. Absolutely comfortable writing this. Okay? Now, this concludes this part. Of course, there's a lot to say about limits, and we're going to keep learning about the rules, and we're going to keep learning tricks how to do limits. But I just want this basic thing to be established today. Now, I'm going to jump to something completely irrelevant, it will look like, to show you exactly just what the application of this is. But I will come back to it. So give me 5 minutes of storytelling, and then we're going to come back and see limits again, okay? We have a circle, and this is the center, right? And I need to draw the tangent, let's say, at, let's say, this point here. So this is point A, and I need to draw the tangent to the circle through this point A. What do? Easy. I connect the center to this circle, to this point, and then I take a perpendicular right here. And that perpendicular will be the tangent. What is the tangent? It's a line that is at the same time very close to the circle. You see here, it's very close to the circle, and it is perpendicular to the radius. Okay. This is what the tangent is. It touches the circle at only one point. It's all right. Don't worry about it. Thank you for coming, Alma. See you whenever you can. So this is what a tangent is. It's a line that crosses the circle at only one point perpendicularly to the radius. This is easy to do. What if I had a function f of x, and this function f of x, I need to know what the tangent is at this point A. Okay. How do I know what the tangent is? It's not a circle. I need to estimate where the approximate circle here is and find the center and do a perpendicular. Nah, this sounds kind of catastrophic here. I don't know what this is. If it were a circle, it would have been very easy. But here, finding the tangent is a difficult matter. Is it this line? Is it this line? Is it this line like this? By the way, look at this line. This line cuts the function at only one point, which is identical to this tangent right here. But it's not a tangent. Do you want to call this red line a tangent here? Never. It's very ugly to be a tangent. So what is the solution? Okay, let me just change the shape of the function so that it becomes clearer. Okay. Let's take something that looks like that. Okay. And then, you know what? Let's even make it easier. Let's call this y equals x squared. So this is y equals x squared. And I need the tangent here at this point B. So I need to draw the tangent here. The clever trick is I'm going to start with a point A, any point on the graph. And I'm going to create a secant. Okay. So this is just a line that crosses the curve at 2 points. But then this point is a magical point. It's not a, it's a regular point. But I'm gonna have this point move all the way towards B. I'm gonna allow myself to imagine drawing several secants as this A is moving. Let's imagine on a sequence towards B. So this A now has x equals 2, let's say. Okay, I'm gonna let x equal 1 here and then draw another line. And then x equals 0 here, and I'm gonna draw another line. Sorry. Okay, and then I'm gonna keep drawing lines here. And you can see that this secant line, as A is moving, this is still A, still A, as A is moving on this curve, this blue line is becoming closer and closer to a tangent. Now, if this doesn't remind you of anything, it should remind you of a limiting process. I'm allowing A to get very, very close to B. But I cannot allow A to be exactly B. Why? Because I started with a secant line. I started with a line defined by 2 points. You cannot define a line only by 1 point, because this is the line, this is a line, this is a line, this is a line, this is a line. All these lines go across this point. Okay? So I need 2 points to define a line. I start with those 2 points, A and B, and I'm gonna allow A to get close and close, closer and closer, infinitely closer to B, without actually touching the letter B. And that is exactly what a limiting process is. Just like here, I'm letting x go infinitely closer to 0 without actually being 0. Here, I'm gonna let this point become B without actually being B. Okay. Now we're getting somewhere. How do we write this? How do we do that to find this tangent? Well, we need to remember, how do we find the equation of a line? Well, the equation of this tangent T here not this one. We're going to call this t now, because I don't care about this one anymore. And this t is just y equals mx plus c, just like any line. Now, the thing is, I already know the point B. Whatever, x, b, y, b. Why do I know it? Because they give it to me. They told me draw the tangent here. I could have chosen any other point on the curve to draw the tangent. They told me, please, I need to know the tangent of this curve on this point B here. That's what they said. So I was given this point B in the question. You can pick any point you want, but as long as you're picking a point, you know what point you're picking. So I already know a point. What I still need to know is I need to know this. Okay? I need to know the slope. Because once I have the slope and once I have a particular point, I can write the equation of this line. The coordinates of this point here help me find C, and I need the slope and I'm done. What is the slope of this line? The slope of this line is just like the slope of any line. I have difference in y divided by the difference in x. Now, I'm happy with having yb and xb here. Why? Again, because I was given this point. They told me what this point is. But I'm not comfortable with having y of a and x of a. Why? Because a is a moving point. It's moving across this curve. And if it's a moving point, it's always changing. And so the slope of this secant line is always changing, and you can totally see it here. It's nearly horizontal, and it's becoming closer and closer, closer and closer to a vertical line as it moves. Okay? So what do I... How do I continue here? Like that's so weird. Okay? I need to find a way to translate what is happening. First of all, I don't know why AXA. Second of all, why A is moving towards B and I need to write it down. I need to figure out a way to write this. Problem number one, we already have a clue. And the clue is here. I don't know X of A, but I don't know Y of A as well, but I know a relationship between Y and X. Why do I know a relationship between Y and X? Because every point of this curve, fits the equation of this curve. If I started with Y equal X cubed, then every Y will have the X cubed that is correspondent to it. If I started with Y equal 1 over X, every Y will have the 1 over X correspondent to it. Okay? And so A, I don't know where it is, but I do know that Y of A, just like any other point, has to be X of A squared, whatever that is. And so I'm going to write this again. I'm going to write YB minus, instead of Y of A, I'm going to write XA squared divided by X of B minus X of A. Okay? So step one, why am I allowed to do this? Because A is on the graph. Hold on a minute. Y of B, even though we know it, is also a point on this graph. So let's get rid of all this and then say, instead of Y of B, X of B squared. Is B not on the graph? It is. So no problem. Okay? Now, we solved problem number one. Now I have only one unknown, which is what? XA. XB we know. So problem number one, we solved. Problem number two, how do I express the fact that these 2 points are coming closer together? Remember that X of B squared and XB are known numbers, but this XA is moving towards B, so that it makes a tangent. How do we express this idea that something is moving towards something else? Well, with a limiting process, without touching it, right? with a limiting process. So I will say that the slope of this tangent here is equal to the limit. So this is not the case. This is not always true here. This is only true for secant lines. For the tangent, the truth is that the slope is not only this equality, but it is the limit as a goes to b of xb squared minus xb minus xa squared minus xb minus x of a. This is the answer for the slope. As a becomes infinitely closer to b, the secant blue line infinitely becomes close to the tangent. What does it mean to be infinitely close to the tangent? It means it is the tangent. Can you squeeze any two lines between the infinitely close to the tangent and the tangent? No. Can you squeeze any point between 1 over n and 0? No. Whatever point you find, you're going to find more points between that and 0. Same logic here. The more you get close to the more a gets closer to b, the more this line becomes closer and closer to being the perfect tangent. When do I have the perfect tangent? When a is infinitely close. Everything is fine, but this a going to b is kind of bothering me. What does it mean for a to go to b? Well, remember here, what did we do? We said x equal 2, x equal 1, x equal 0, x equal minus 1, minus 2, and then we kept going. We made a sequence that goes to b. So from x of a here, from this number, x of a, you keep making points until you reach b. So instead of a going towards b, which is not a sort of mathematical way of writing it, what I'm going to write is x of a is going towards x of b. And as long as x of a goes towards x of b, and as long as a and b are on the same curve, which they are, I'm guaranteed to get my tangent. I'm guaranteed to translate like that without losing any information. If x of a goes to x of b, and we are on the same curve, then y of a is also y of b. Because y of a is x of b squared, y of a is x of a squared, and y of b is x of b squared. So if this becomes that, then we're fine, okay? That was a load of English for a simple idea. So instead of a going to b, I'm gonna write x of a going to x of b. And here is where the magic happens. I'm gonna remember now that this becomes x of b minus x of a multiplied by x of b plus x of a. Why? Because remarkable identities. Oh, I'm so happy that we've learned this before now. Okay? Because of the remarkable identities property. That's why x of b minus x of b squared minus x of a squared becomes this. Okay? And now, since I have the same equality here, x of b minus x of a, x of b minus x of a, this is a positive number. It's getting smaller and smaller as a goes towards b, but it's always a positive number. Okay? Because a is never allowed to be actually b. And so this number gets cancelled out. And then you're left with x of b plus x of a. And what is the question initially? The question is the limit as x of b becomes x of a of this quantity. Well, if x of b becomes x of a, then this is x of a plus x of a. And this is 2 times the x of a. And because a is just simply any point on this curve, instead of saying x of a as if we know, we don't really know, so it is actually 2x. We have started with a function that is equal to x squared, and we have reached 2x. And if this doesn't look familiar, it should, because you've probably learned that the derivative of x squared is 2x. And that's exactly what the derivative is. The derivative is the answer for this slope. The slope I'm looking for this line here, for the tangent, by definition. We looked at this and we said, oh my God, look, this derivative, this finding the slope thing, it's an interesting thing, so we're going to give it a name. and we named it derivative. Okay? It's always has to do with starting with another point on the graph and then dragging that point, dragging it until you make the ideal tangent to the curve. And in the case of a function that says x squared, the answer for that is 2 times the x that you started with. Okay? Or the one that you've ended with, actually. The xa and xb become the same. This is what a derivative is. Okay? So to take an example, let's say I have the function, the same one, but I have that the point b is, let's say, minus 2, 4. Okay? And I need to find the tangent at b. I have that the tangent is y equals mx plus c. What is m? M is 2 times the x I started with. I know that now because I did the math. So m is equal to 2 times x of b. And what is that? That is 2 times minus 2, which is, let me write actually, 2 times minus 2, which is minus 4. So now I'm going to say this is y equals minus 4x plus c. But now I remember that this point B is also on the tangent, because that's the definition of a tangent. The point is always on the tangent here. And so I'm going to say y of B, which is 4, is equal to minus 4 times the x of B, which is minus 2, plus c. And 4 is equal to 8 plus c. C is equal to negative 4. So here the equation of the tangent is y equals negative 4x minus 4. With limits and with derivatives, it becomes a piece of cake. Okay, so I solved this limit already. I don't need to do the work again. This is why the derivative of x squared is 2x. And now I'm going to leave this on the board for a second. And I'm going to go towards my computer. And I'm going to let the equation x squared just to show you guys. And I'm going to pick on the graph the point minus 2, 4, which you see here. Okay, so we're going to call this point here point B. And I'm going to pick any point A here like we did. And I'm going to let the computer find the line between A and B. And look at the line equation right here. It's an ugly equation. Let me see if I can force the... Yes, I can force the computer. It's an ugly equation. Now, as we said before, I'm going to keep B fixed, and I'm going to let A go towards B. Okay? So A started here. It can start anywhere. But the point is I'm going to get it closer and closer to B. And notice that as I'm getting it closer and closer to B, the secant line, the black line, is becoming closer and closer to a tangent. And as I get A very, very, very close to B, notice what happens. Are you looking at the equation of the line? This is still a secant. You cannot see that it is intersecting the line because we are very, very close. Okay? And I'm going to keep going up. I'm going to keep going up. And look at the equation. Look at the equation. Look at the equation. Minus 3.97. We had minus 4 on the... we had minus 4. Minus 4. Look, minus 3.7, minus 97, and then 994. Okay? And then I can keep going closer. I can keep going closer. And the closer I get, and I can keep zooming in, which is the beautiful thing about GeoGebra, by the way. And I can keep zooming in. And look at this. I can get infinitely close. As close as I want. And now when I zoom out again, look. I'm gonna make the points disappear so you can see. This totally looks like a tangent. This is the tangent I'm looking for. It's still a secant. I can make the 2 points show and I can zoom in. And of course, again, in real life, I can never do this because this is a process that requires me going to infinity. Look, the more I zoom in, it's not zooming. The more I zoom in, the more I can zoom in. The closer I can, the closer I can get. There is no end result here. There is no end for this process of getting infinitely closer. The name suggests it. I'm getting infinitely closer to B. How can I ever reach B? Okay. But I'm not gonna go there myself or let the computer go there. By the way, the computer doesn't like going there. It will blow up. Okay. But what I'm gonna do is I'm gonna do some clever calculations like I did here. And I'm gonna say, what happens if we had the capability of going to infinity? And what happens is you're gonna get to minus 4x minus 4, which is exactly what we have. Okay. This is the importance of limits. The importance of limits is they help me solve problems that are difficult. This problem right here is a difficult problem. Remember, this is what we started with. We started with any function on the planet. And I'm saying any point here on the function, calculate the tangent. In this point, calculate the tangent. Here, calculate the tangent. That's a difficult problem to solve. Find the exact line that is the tangent to the curve. Drawing doesn't help. I just showed you. Look. If someone drew this line, they would think that they found the tangent, but it's not actually the tangent. This is a very close line to the tangent. It even says it on the computer here, minus 4x minus 4. It isn't. We know it isn't because the 2 points are not the same point yet. They are just getting very, very, very ridiculously close. They're just not the same. You can't become the same. You will create problems. You will get infinities. You will get zeros. You will get ugly stuff. Okay. So without limits, this problem is impossible to solve. But with limits, it just becomes a piece of cake. It becomes a walk in the park. After we've solved that, the slope of the tangent, which is what we will call derivative, after we've solved this problem and found that in the case x squared it is 2x, it becomes a piece of cake. Finding this line becomes a piece of cake. And without limits, I couldn't have done it. So this is it. This is it. This is the genius trick that we've learned today. This is calculus. This is the world of infinities and infinitesimals, very, very, very big things, infinitely big, and infinitely small things. And this is why people went there to begin with. This is not to torture students in exams. This is a clever trick to solve problems. Of course, more on this in later episodes. We're going to keep doing limits, we're going to keep doing calculus, we're going to keep doing derivatives. We're going to keep trying to solve problems and figure out what they are. You cannot do anything in physics without calculus. There's nothing you can do in physics. In the real world, people always ask for real-world applications. There's nothing literally you can do in physics without calculus. Nothing. It's such a powerful tool. And now you are initiated in it. So enjoy. I think this is enough for today. We're gonna pick up at a later date. Hopefully on Saturday I'll have another stream. From now on, from now till then, I wish that you stay very cozy and very warm. So thank you very so much for being here, and enjoy the music while I send you off. Go have fun, drink hot chocolate. See you later. Join our Discord if you haven't, and follow our YouTube. Take care.